What's up, everybody? Welcome to Flux Harmonic. I'm David Wilson, and today we're back with another live stream where we try to build something cool from scratch. And today is no different in that we are going to try to build a pretty important language feature from scratch. We'll see how successful I am at it, but it's something I'm very excited to implement, so we'll get started on that in just a moment. So basically the idea is that we want to implement tail call optimization in Mesche to enable loops. I'll explain a little bit more about what I mean by that, but it's a pretty cool feature, and we'll talk about that in a moment. First of all, I want to say that a lot has changed in the Mesche world since the last stream. I've done a lot of work to try to break out Mesche into its own GitHub repository, where I'm building the compiler itself outside of the scope of Flux Compose, like I was doing before. I kind of like had started writing the code integrated into Flux Compose. Now I've ripped it out into its own separate repository. You can check it out on github.com/mesh-lang/compiler. There's also a CLI repository, which is basically the command line interface for the compiler. And I'm still just debating on whether I want to have those two things separate because it's easy for them to get out of sync a little bit. But the idea was that I would make the command line interface be like the first consumer of the library for the compiler, and have it be something that gets shipped separately. But we'll see. I might change that. I might make it just one repository to keep things simple. But at least for now, I'm very happy to have those things up on GitHub as a separate project. And let me actually just take a look at that repo. Whoops. Once again, I blasted my stream key on the stream. It doesn't matter because I'm already using it, so I don't think anybody can take it. But anyway, this is the repository for the Mesche compiler, and it's just the code that we've been working on so far. And I've got some CI set up for tests and whatnot, so everything's good there. I've also got the CLI repo that you can take a look at, which is a little bit less interesting because there's not much there, but it's just the stuff to build the command line interface for the compiler. One interesting aspect of this, at least for the CLI side of things, is that I'm building this with a C standard library called Muscle C, which is meant to be statically linked into the target application. And what that means is that you can basically take a binary built for Mesche and run it on any Linux system, because it doesn't depend on the system's GNU libc, which is kind of nice because you can take it on even on a Geek system and run it directly without having to have anything special installed. So that's one way that I want to try to distribute this compiler, is basically have this statically linked compiler that you can run on any system. If you've ever used the Zig programming language before, this is something that Zig also does pretty well. So I'm kind of following that model because I like it, and we'll see how far we get with it. Let me just check one thing really quick, make sure. Okay, yeah, I think my voice is coming through. So we'll talk about that more as time goes on, but I just wanted to sort of point out that we have these things set up now in case you want to take a look at those projects. Also, added basic record type support. Hey, Bill, don't worry. I'm a little bit late too, so what can I say? So I added basic record type support to Mesche. If you don't really know what record types are, it's basically like structs, but in a scheme or list type language. So you basically just have the ability to define a record type, which has fields, and you can create an instance of that record type and set the values on the fields. For now, this is an immutable record type where you can't change. Hey, Daigo. You can't change the values of the fields. But that may change, but for now I'm just keeping it immutable because, you know, I want to see how far we can get with just immutable structs or record types. I do plan on making an actual struct type that follows closely to how C structs work to have better performance and access to direct access to C structs without having to have any kind of wrapper type. Hey, Emil. So that's something I'll add a little bit later. I have some ideas in mind for how to do that, and I'm kind of excited about having that capability because that means that I could write more high-performance game code or any other kind of code in Mesche itself and not have to do as much mapping between Mesche and C whenever I'm trying to wrap APIs. I also improved the module system. So I probably should go in a different order, but while I was working on the record types, I was also trying to work on a project system for Mesche so that the command line tool can read a Mesche project file and then build a project with both Mesche and C files. And during that process, I ran into some limitations of the module system, or I guess you could call them bugs, where depending on when you first load a module, it affects how the exports of that module are actually pulled into the module that imports it. So I had to do a little bit of rethinking and rewriting, and I finally got things working again the right way, so I'm happy about that. But it did impress upon me the need to start adding unit tests, because I didn't have any unit tests before, and as I add new features, there's regressions coming in, and I don't have any visibility into when they're happening or why they're happening. So we now also have a unit test harness and unit tests for, or I guess basic unit tests for all the different components of the compiler. So another thing I added, mainly as a result of this issue, the issues I've ran into with the module system. So let me just show you what I was doing with the project record type and whatnot, because it will show you a few different things at once. So if I go into the CLI project in modules mesh CLI project, let's see, let me just make this be a scheme mode buffer. So you can see here that we are defining a record type called project inside of the mesh CLI project module, and we are giving it a certain number of fields: name, URL, version, description, dependencies, inputs, and outputs. Now, the intent of this is to have a way to describe a mesh project so that it can be run through a build tool. So an example of a project file like this can be found in the Mesh CLI repository as project.msc. And you can take a look here where I'm actually calling the constructor function make project and passing in keyword value pairs for all of those fields to populate them. Now, this is not the syntax that I want to have for someone writing a project file. I actually want to have a macro that wraps this and give it a bit cleaner syntax, but I don't have macros yet, so we're still just going to write these things directly for now. But you can see that I have like the name of the project, the URL of the repository where you can find it, the version number, which is sort of bogus right now, description, also the dependencies, which is kind of important because this defines the mesh dependencies that need to be pulled in to make this project work. This doesn't work right now. None of this really works, but the idea is that you would have a list of dependencies. In fact, this probably should just be a list here. And the fact that I'm having to quote this list is an indication of the fact that this needs to be a macro. But you could have multiple dependencies, like let's say mesh, I don't know, process or something. I don't know. These would be different repositories that need to be cloned down and compiled as part of your project. So that cloning and building is part of what the mesh build command needs to do. So it's something we will add. IO control says, will dependencies be versioned? So I want to take a more, I guess you could say Go-like approach or Dino-like approach where you're going against like git commits potentially instead of versions. I mean, obviously I have a version right here, which is sort of like a nominal version in the sense that, you can tell what, you can gain some information by reading what the version is, but there won't necessarily be a central module repository that has a listing of everything, all packages in versions. There might be, I don't know, we'll have to see. It's a matter of things going over time. But for now, at least, we're going to pull them from Git repositories, which does imply that we're going to have some way to have like a commit and some, commit hash effectively there. So that's something we'll look into a little bit later, but at least for now, I'm sort of sketching out what I want this to look like, and we'll implement this behavior a little bit later. Also, inputs, you can have both C or mesh inputs. Doesn't work right now, but sort of the idea. And it would build all of the C files and all of the mesh files and then compile them together into a binary, which does mean that part of the goal is to store the bytecode compilation output of each mesh file and then integrate it into the target binary so it can be loaded from within the binary and not have to have the original mesh file sitting around. It doesn't work right now, but it's something I want to get to really soon because I think it's a pretty cool feature. Also allows you to have a fully statically linked binary that you can ship. Like for instance, a game that I don't want to have a bunch of mesh files sitting around in the game folder. I just want the binary and then whatever assets are necessary to run the game. Then the output file, which is just bin/mesh in this case. So I've already implemented sort of the behavior that I want in this build.sh file. Like I went and wrote a whole bash file that implements the behavior that I would like to have. And I think for a first pass for writing the build command, what I'll end up doing is generating a bash script from mesh and not trying to write all the code to do all the same things because I want to get things running fast. So I want to basically take the project definition, generate a bash script like this, and then run that to do all the tasks necessary. And then eventually add more functionality to Mesh to make it possible for Mesh to take over and run some of these things. Obviously, we're still calling it to GCC, Git, etc. And I'm also downloading the Muscle C toolchain as part of this so that I can build that statically linked binary. This background music is starting to get a little bit annoying. But yeah, I mean, eventually Mesh will take care of all that stuff. But for now, what was this playlist? Okay, cool. So I actually had something I was working on here. But for now, we will just generate a bash script to do that. But we're not doing that today. We're working on something else today. Let me just get back to where we can listen to some music that's not going to drive us nuts. This isn't much better. I wish I had better music for the stream. That's something that we'll work on in the future. But for now, at least, we're stuck with what we got. Okay. So that was sort of the walkthrough. Now, let me just, hey, Alex, mention a couple things about the record system, just because I think it's kind of interesting. And this is basically ripping off what Scheme does, but it's something interesting to me, at least for the implementation of this language. Let's see, project.msc, this one. Okay, so when you define a record type, what actually happens is we define a record type in the language. It's an object that's stored in the language, basically. But we also are dynamically defining functions to for the constructor of the type and also for the accessors for each field. So if you go into the, let's see, init.msc file here, I need to get scheme mode wired up. You can see that I actually pull in project-name, which is actually a generated accessor function for the name field of the project record type. It's actually kind of nice because it means that we don't have to do a dynamic lookup of the key in the record type so that we can index into the actual instance of the record to get the value out. We actually have a pre-made function that knows exactly how to pull that value out. So in theory, it should be fairly fast to call these. These are their own special type of callable, which means it's an object that can be invoked. And when you invoke it, it basically just rips that value out of the array holding all the values for that record instance. And it has each accessor function has the index of the field for that record type hard-coded so that it knows exactly where to pull it out from whenever you try to access it. So I haven't done any benchmarking yet, but I'm thinking that it's going to be pretty nice whenever I start using this in real practice. Also, I've got this init.msc file for the compiler. This sort of shows that we've got enough code to have like a very, very basic entry point for an application written in Mesh. So one other thing that's kind of interesting is that I've added process arguments. So I have a function called process arguments, which will return a list of the original arguments used to launch the application. And then you can use like the list nth function to pull the first argument and then check it to see if it's build. And if it's build, you go to run build. Otherwise, you display help. I need to do a lot of work on the printing functions to make the output look better, because if you were to go into this shell right now and run bin/mesh, you'll see that I've got all the new lines kind of baked directly in, which is not what you want in real printed output. So Travis says, are you eventually going to re-implement records with macros instead of having hard-coded support in the compiler? It's possible, but I need to determine whether it will affect performance negatively. I mean, it's kind of nice to have them in the compiler, but you could definitely conceive of there being like macro level support. So it's a good question. A lot of stuff that I'm doing right now definitely are begging for macros, and I just haven't gotten to that yet, but it probably won't take much longer before I do get to it, because it's something that you really need to make this language more elegant, I think. Part of the reason for making a language like this is that you write some very nice primitives for things like, functions, record types, tail recursion, like we're going to work on today. Let's see, what else? Just various different things that are necessary for just sort of basic computation. And then you have the macro layer on top that allows you to invent new syntax to do more interesting things. So I kind of like the way that Scheme works in that regard, and that's why I've sort of went with a Scheme style language. All right, so let's see. Let's get back to the slides. Anything else? Basic CLI interface for Mesh and the first Mesh program. Yep. So I'm pretty confident in what's been done so far. That it's going to work for the stuff that I have in mind. There's going to be a lot of work left to make it a legitimate language, but I mean, I'm not really intending for this to be used by many people. I'm just sort of doing it for the fun of this channel and the projects I'm making. So we'll see how these things go over time, but I'm pretty excited about it nonetheless. All right. Today, we're going to try to implement tail recursion in the language, mainly because Mesche does not have any kind of a looping construct currently. And I didn't implement one up until now on purpose because I knew that that I wanted tail recursion as the way to implement loops, which is basically what Scheme does. Scheme depends on tail recursion to do looping constructs. Now, if you don't know what tail recursion is, it's basically when, or I guess tail call optimization is the real name for this. And that gives you a little bit more of a clue about what it is. It's an optimization in a compiler where if you define a function and the function calls itself as the last thing in the function or the last thing that happens in the function, you can basically just convert that into a loop instead of it being a recursive function call, which means you no longer have a new entry on the call stack. You don't have to worry about Stack Overflow problems, that kind of thing. So if you implement tail recursion and it's easy to write a function that qualifies as being tail recursive, then you can use tail recursive as your core looping primitive. And then you can have things like a macro that can turn any other style of loop that you want into that core looping primitive. So what we want today is to basically attempt to write a tail call optimization in the Mesche compiler, at first by adding functionality to the compiler in a test-driven way. So we're going to try to do this sort of, by instrumenting it first with unit tests, and then once we sort of see the output the way that we want, then we'll try to use real code to execute those. And we really need this so we can have like a game loop. Like if we're going to write game code in Mesche, we need the ability to have a loop, because the main loop is sort of the most important part of a game engine. You need a loop that can do all the things like updating all the state of the entities in the world, rendering everything, checking input, all that kind of stuff. So that's the reason why we're doing this today before we get into any actual game development, because we need a way to make a loop. Alex says, it's opinionated printf, new cargo cult incoming. Yeah, we'll see. So, excuse me. So we're going to follow the pattern of scheme style named let, because I find it to be a very versatile pattern for writing loops. And it's effectively a specialization for normal tail recursive function definitions, and probably scheme implementations turn named lets into sort of like an inline function definition that is recursive. So by implementing this, we're basically going to get to having generalized recursive function calls working for free, I guess. Some examples of scheme style named let. I wanted to put these in here just so you can see what I mean when I say it's very versatile. First of all, a named let is a let expression. A let expression is normally used for binding new local variable names to values. So normally you would have like a let with like an I bound to some value. A named let is the let where you actually have a name that is being used for that let, so you can refer to itself. So we have a let here named count loop with a variable called I bound to 1 by default. Then inside that body, we have an if that checks to see if I is less than or equal to 5. If it is, it runs this little begin block to display what the value is, and then to call itself using I plus 1 as the new value. So whenever you're running this loop, because it's tail recursive, because the last thing that happens is this recursive call to count loop, it basically turns into a loop where this value that you pass to count loop actually just replaces this binding of I here, and then it just starts over the execution of the body of this let block. And then at the end, once it finally reaches 6, I guess, then it goes to the else block. It says display done, writes out the done string, and then it doesn't call itself again, so it's no longer recursive at that point. So if I were to go into Guile and paste this in, you can see how this works. So I'm just going to go copy this code, go down here, paste it in. And then you can see that it just ran this, still not there yet, 1, 2, 3, 4, 5, and then done. So that works for just a simple like for loop where you want to increment an index. But what if you have like a list of values that you want to loop over? In this case, we have a loop called list loop, and it has a vals variable that's bound to a list 1, 2, 3, 4, 5. First, you check to see if the vals list is a pair, which means if it has a car and a cdr, then you can consider it still part of a list. Then you have the begin block, display still not there yet, write the value out. Why is this lowercase still done? That's weird. Anyway, follows basically the same pattern, but this time it's looping over a list of values. So if I were to copy this and run it, then you basically have the same type of behavior because it's the same type of loop. It's just, you're looping over a different set of values in this case. So it's very versatile in that it's a very simple pattern, but you can do pretty much any kind of looping construct that you want with it. And also, because it's tail recursive, you can loop infinitely because you're not consuming new entries on the stack frame list. So we have this infinite loop let block, which basically just starts at I of 1 and then just loops infinitely. It never checks to see if it needs to stop. So if you were to paste this in, you can just let it run, and it's just going to run forever because it will never cause a stack overflow, and it will just keep looping over itself over and over and over. It's just jumping back to the beginning and starting again. So this is the kind of behavior that we want to try to implement because this will be a good starting point for any other kind of looping behavior that we really want. Alex asks, does a program keep those calls on the stack? No, just the first call to the function, and then it just basically operates like a loop. So that's what we're going to try to implement in the compiler. All right, so the tasks for today then. First of all, we're going to write up some notes on what we think the design should be, because I haven't done this before, so I'm going to try to think through it a little bit. I've thought about it a little bit already, but might be interesting to sort of show the process of like writing the ideas up and then trying to implement it. And then we're going to add compiler support for named let expressions. So we've already got let expressions in the compiler, but I just need to add named let support so that we can move on to the next step, which is to add a unit test for checking named let compilation. So however we decide to implement named let, we need to have a unit test that can make sure that the output of the compiler for such a let block is what we expect. Then we can start implementing tail call checks in the compiler to identify a recursive call that can be turned into a loop effectively. Then we're going to update the test to verify that tail call checks are being compiled correctly. So we basically found a recursive function call and we turn that the output code into a loop instead of a recursive call. Then if we have time, which we probably won't have time to get to all of this anyway, but if we have time, we'll try to generalize tail recursion implementation for all function definitions and not just for named lets. So we're starting with named lets because that's the way we're going to loop in many cases in the language, but in a lot of cases you will also use function recursion too. So you'll have a defined function that needs to do its own recursion, and it's a very common pattern, so we need to have that as well. All right, so we're going to start by writing up some notes about how this should work. So first of all, a named let should create an entry in the locals for the function, for whatever the scope that the function is. So if you want to call the function again, we need to be able to identify that that a name being used in the body of the function is actually that same function. But we don't really know yet whether we are we checking the symbol or the value. I guess really it's the symbol because we don't have runtime access to what that function contains or what that symbol contains. So we're using the fact that we have a named let. We know this is a named let because we're defining that local variable in the scope. So when we see that variable again, that local variable, we're like, okay, so it must be a self-reference. So when we see that, then we can make a choice about whether this function actually qualifies. Have a heuristic for whether the block is tail recursive. And I guess the question is, how would you do that? Because this is a language full of nested expressions. So like you see that if expression I showed you before, we have count loop right here, and count loop itself shows up down here, but it's nested within an if statement or an if expression and also a begin block. So we have to be looking for this count loop all the way down to this level. So we have to think of a way to sort of track what the name of the current scope is, what the current let block is, so we can check for that later. And we need to do this in a way that can be easily generalized to a function definition as well. So, excuse me, we may need a way to sort of mark the current function. So mark the current closure with the closest function let local slot, maybe. I don't know. We'll have to see how this shakes out in development, but we may not get very far with this today. I mean, this is going to be my first time doing this, so we'll see how it goes. And then once we have that, let's see, when we find that function, so at the location where the function let name is called, we have to decide how to emit the bytecode. Is it a jump or a function call? And that's going to be the most important thing here. Is like once we recognize that we're calling the function recursively, how do we convert that into a jump instead? We're going to have to keep some state probably to know where we need to jump back to. So this is all going to be very interesting, and we will try to see what we can do. I don't know the proper way to implement this, so we're going to do it the stupid way, or the obvious way, or the naive way, I guess you could say. And then later I might go look up like the literature on how to do this correctly, and then maybe update it if necessary. So we'll see what happens with that. Anything else we need to consider here? I think that's basically it. So that's what we're going to go with for now. We can call that task done. Bill says, OCaml has let rec for recursive functions. Yeah, so it's going to be a similar thing here. Alex says, I like how you take these notes. They're for our benefit, but they also triage. Yeah, I mean, it's worth to try to write these things down so that I don't forget what I was planning to do while doing this stuff live. Okay. Excuse me. So first of all, let's jump into the compiler code, and then we are going to try to add that named let support. So we'll go into source/compiler. We have a parse let, I think. And inside of here, we create a new scope, which is good. And I need to refresh my memory on what that does. Okay, just increments the scope depth. That's fine. So we start by looking for the binding pair, but we can actually find the name of the let. The name of the let. Yeah, okay. So if context parser current dot kind equals token kind symbol. Probably also should check and if context parser current dot kind. Well, no, let's do this first because I might need to give a better error if something goes wrong. So then we can parse that symbol if that the subkind is a new concept that I had to implement. I can't remember why now, but a symbol may have a subkind. Hey, Venkatesh, thank you a lot. All right, so if the subkind is not equal to token kind none, which basically means this needs to be a pure symbol. It can't be some other kind of symbol like let or define or something like that. Then we might need to give a compiler error. All right, so compiler error used an invalid symbol for named let. I need to improve these errors at some point, but for now, we're just going to go what we got. So now we can just parse the symbol, basically. So let's see, object symbol let name equals null. And then here we can say let name equals. Now, do I have a function that returns that? Let's see. Let me just put that there for now so that the code formatter doesn't totally screw up the file. Symbol literal. Yeah, that doesn't return one. So let me think about that for a second. We need to be able to parse that. Parse keyword literal, parse string literal. Okay, so symbol literal, for whatever reason, I don't have that one returning the string. Sorry, the symbol. These do, though. And they also don't emit a constant. Where am I parsing? Parse symbol. I think there's another function for that right there. All right, so We might want to copy this a little bit. Yeah, this is terrible, but we're just going to do this to get it moving, and then we'll fix it up a little bit later. So we're going to call just mesh object make symbol. We're going to return that. Join that line, take out these two parens, and we're going to make this return object symbol. So this is basically just going to parse this symbol and return it back because we need access to it. So then we'll go back to code we were at, parse let. And then here we can use compiler parse, parse symbol literal 2, terrible name. And that should give us back the name of the let. And let's just print it out so that we know we found it. So found named let. And then we will say let name string dot chars, which is basically how we have the stuff encoded. Now, we can go into the unit tests for the compiler and add a new function for compiles named let. And I'll add a new function for that. So the unit tests are very simple. It's similar to what we were doing in Flux Compose, where we just have a very simple test harness to exercise this stuff. Our compiles named let. Now we're going to have an example of a named let here. So let test let, I don't know. And then we need the binding section, so I1. And then we can have another string here for plus I1. I don't know. Let's just do that for now. And that should be sufficient to test compilation of this. So what we think is going to happen here is that the compiler is going to not emit this symbol, which we might want it to actually, to define the local. But probably what I should do is just check the output and then start writing tests around the output, which is not the best way to do this, but, you know, mea culpa. So let's do that. Let's just turn on the debugger for the compiler right here. I'm going to go and uncomment this line, debug print code, because I want it to write out the code that's being compiled. Then in the compiler folder here, I'm going to run, well, let's use compile for that. Let's jump up here at this level, compile. We're going to run geek shell. Ooh, yeah, I need to pull the right one for that. Let's see, run tests.sh. And then we'll go / manifest.scm for that one. Let's see if that works. Yeah, sure. Okay, we're going to pull some things down using geeks for a second. Alex says, these tests are so cool. I can't see how I would meaningfully add tests to my game engine. Going to have to think about it. Well, there's always stuff that you can test. It ends up being stuff that is that returns clear values. And a lot of times helper functionality or anything library related can do that. So you can test a lot of stuff like that. All right, too few arguments. I think I forgot something in my compiler error call. Let's see, let name. Yeah, okay, so compiler error here. I think I need to pass in the context also. Okay. So error at test let, expected left paren after let. Interesting. So we've already got a little bit of an issue. Let me go up to, let's see, left paren. Okay, we don't want this to be run yet. This is looking for the beginning of the, yeah, so we'll do that here actually. We'll copy both of those. So we're looking for the beginning of the binding pairs a little bit too early. So we need to do this before. The name needs to be looked at before that. Error at test let, expected left paren after let. Why? Oh, because I didn't actually advance the compiler. Compiler advance. I need to move to the next token before I try to do that. Okay, so now it's happy. So let's see what the output is. All right, so which one is it that we're looking at here? There's a few different things being run. Maybe we should just focus on the compiler test suite for now. So let me, I don't have a good way to highlight specific tests. So I'm just going to comment some things out. Test main, let's see, test main. Let's get rid of the scanner suite and the VM suite just so we can focus on the compiler test for now. Okay, so this is just the one test we're looking at. So there's a constant of 1, read local. Okay, so that's for the local variable. And we're popping scope twice, which is interesting. Yeah, that makes sense. Okay, so, oops. Let's go into test compiler again and then take a look at this. All right, so the constant is the 1, obviously. We're pushing the 1 constant in. Then we're reading the local, which the 1 is not the 1 constant, sorry. The 1 is the slot for the local variable. So the local variable is I here, and it has a slot of 1 because all variables start with the slot of 1. Then we're reading a constant, we're pushing a constant again. I think it's for setting. So already this doesn't look right. I don't know what's going on with that. Maybe we have some bugs from previous changes that have been made. So maybe first of all, let's see if we can do a little test to check a normal let, which probably is going to have the same behavior. Let's just do it like this. So let's see, let I1. How about this? X1, Y2, X plus Y. That will give us a little bit of an insight into what's happening. So I'll add that compiles let. So now we'll have both of these. All right, so the first one, constant 1, constant 2, read local. See, that doesn't even seem right to me. So there must be a bug here already. I wonder what would happen if I executed these. I guess I can check that out inside of the VM test even. So if I were to copy the same thing, let's go to test VM. Test VM. All right, so we're gonna have a static void VM evaluates let. And we will say VM init here because we're going to initialize a VM eval to eval the same source code. And then at the end of this, we would expect to see, we need the interpret OK here as well. We would expect to see a 3 as a result. That's how we're going to do this. We're going to check and see if it returns 3 or if it does something completely unexpected. All right, so assert object value object kind number. So after executing this, we expect to see a number at the top of the stack. And then we also want to see if, let's see, as number value is not equal to 3, then fail it wasn't 3. So that's how we're going to try to check that. Then we can say VM evaluates let. And we'll comment those out too, just to keep it clean for now. Go in test main, we'll go back and run the VM suite too. So let's run that now and see what happens. All right, so we have a little bit of a problem here. Object kind number undeclared in test VM. I think object kind, oh no, it's not a number. So it's a value number. And we're gonna use assert kind for that, I think. Do I have that macro? Okay, actual kind, expected kind. So let's go down here to where we were. And then assert kind, value.kind. And is that the right order of yeah, okay, let's do that again. VM eval requires 2 arguments, but only 1 given. I think I missed a comma right there. Oh, what happened to this eval? It ate one of my strings. Test compiler, let's go back and grab this. Yeah, I stupidly deleted that. Paste that there, put a comma there, okay. I don't like that you're doing that. Silly code formatter. Pass 3 arguments, but it takes just 2. Oh, that's because it shouldn't be a comma, that's right. This is a comma though, for sure. All right, that time it didn't try to fix my stuff. Value undeclared. What did I call it? Yeah, all right, so I need to put that value right here. Okay, So value stack has been popped below initial address. Something is definitely going wrong in the let implementation code. So we might have to fix that a little bit first. All right, so yeah, we're popping scope too many times. I'm not exactly sure what's happening with that, but we're gonna have to go take a look at the compiler output. So constant 1, constant 2. So first of all, we're not binding the variables correctly out of the gate. We need to be setting those locals first. We're not reading those. We need to be setting them for sure. I don't know what happened with that code path. So let's go back to parse let. And then, interesting, my tab bar is not on. Tab bar show mode. There we go. Got to keep an eye on the time. All right, so OP constant gets written out for the symbols, I think. So let me try to write some prints out here to trace this a little bit. Alex says, yesterday I had an intervention on a peer at work who had the wrong linter set. It was like dueling banjos. Yeah, it's definitely not good if you have a competing linting configuration with someone else that you work with. All right, so we have the binding pair starting. We advance, we try to parse the symbol. Now, what is that false there? Parse symbol is global false. Okay, so we're parsing the symbol, then we define the variable. So let's check parse symbol, make sure we didn't break anything in there. Parse symbol. Whoops, I don't know what that did. Okay. So if scope depth is greater than 0, we return, if not is global, and. Okay, so this should go into this declare variable and then not. Let's do this really quick. Printf, parsing a local variable. And then declare variable. Printf about to declare a variable. I like to yell at myself so I see it very clearly in the console. So let's take a look at how this goes. About to declare a variable, parsing a local variable. So that does seem to be going to the right code path for locals. We're looking for an existing local to reuse. And then we get down here, printf. Well, let's just do it in the add local function. Add local. All right. Add local. I'm having issues in my language server. That's the reason why I'm not jumping straight to the definition. All right, so printf about to declare the local. All right, so we're down in this code path where we're trying to declare the local. All that seems fine. So it must not be in this code path, the problem. So parsing symbol, we declare, and then we go back here. So I think define variable is the next one that we're gonna look at. So parse let. We parse the variable, we parse a symbol, which covers that code path we just went through, and then we define the variable. So define variable. We call into this define variable ex, compiler context, variable constant, define variable ex. Okay, I think I know why this is happening because I added some stuff in this code path recently and I must have broken it. This is why I need unit tests, because obviously things like this slip in very easily when you don't have any coverage. All right, so define variable 0, variable constant 0. All right, we want to look at this define variable ex function right there. If scope depth is greater than 0, we want to mark it as initialized. And I have this to do to myself. Is this necessary? Well, probably is. Okay, so defining local, so that did get written out. So we are on this path. Mark initialized. If scope depth is 0, return. Otherwise, we need to mark the latest local variable as initialized. So we set the depth, basically. This may not be necessary. In the book that I was following for this, it sounded like this was only needed for languages that could have a variable that wasn't being initialized immediately at the place where it was being declared. But in the scheme style language, we don't have that problem because the let has the value right there at the time that you declare the binding. However, maybe that's not true in all cases. So I left it in for that reason. Let me just take that to do out because we don't need that anymore. All right, so we followed this code path. We got to mark initialize. Now, we've initialized the local. The local's there. So what's the problem? We're in this function. Parse lambda? No, we want to be in parse let. All right, so after we define, then we parse the expression. So where are we calling read local? Parse identifier. Parse identifier. So where is parse identifier happening? Just there? Interesting. Compiler parse expression. This is in parse set. Okay. Maybe that's why this is not working anymore. Because it seems the only place where I'm calling parse identifier is in parse expression, but it needs to be here too. Parse identifier. Pretty sure. So hold up. Parse identifier. What does that function do? Resolve local. This is only for reads. How do we even get to that point? That's kind of... Oh, no, that makes sense. Okay, so let me think about that for a second. The output that we saw, so read local is wrong in that case. We need to be setting it. I don't know where set local is being called. Parse set. That's very interesting. Parse set. So strangely, the let seems to never have been calling that set, which just seems wrong. Like I think that was working in the past. Okay, so then OP set local, compiler resolve local. If there isn't a local, use a global variable instead. I think there's some code reuse that probably needs to happen here. This is not what I intended to spend my time on, folks. I'm sorry about that. I didn't realize that I already had bugs in here that need to be resolved. But maybe we can make some progress through this and then we'll have a better position to work from. Okay. So we need to call set local. And we know it's not an up value because this is not from a closure. This is a local variable. So we're just going to call set local straight up. Parse expression, emit bytes, instruction, and arg. And the arg is going to be the index of the local, I would imagine. So we need to emit the bytes for setting on that. That's going to take whatever that value is. So the thing that we're not doing right now is let's see, parse let. Come on now, parse let. Can't even type. All right, so right about here where I typed in that parse identifier, which I'm going to undo now. Define variable, that's fine. Parse expression, and then the thing that we're missing here is to emit the set local. So the OP set local. And do we have the index of the local? We need to have that. Is that in, let's see, define variable returns that. So uint 8t local equals, then local. Now, let's double check that to make sure this actually does what I think it's supposed to do. Define variable. Let's see if it's local. Yeah, what? I got a feeling that doesn't actually return anything. What do they just look at? Define variable. How did they give me the impression that it returns an integer? Is that in the header? No. Static function. Okay, so we need a way to get the local compiler. What does it just tell me? Compiler parse symbol. Ah. Now, what is that? Arg is -1. Compiler resolve local. Parser previous. So I may need to just follow this. If arg is -1, then there's not a local with that name, but we know there should be because we just added it. So compiler resolve local. So that looks for the local, but we're defining the local. We need to have declare variable. At this point, we have the local index, add local, has the local index. This probably should return a uint, uint8t. And then we're gonna return the local count -1, because that's the one that we just added. So compiler add local, that can be returned straight through. There's a return here also. Return I. And this declare variable can now return a uint8t. Declare variable is being called in parse symbol. So what is it returning here? So it returns a constant value. Yeah, this is getting a little bit messy. Not very thrilled about it. Parse identifier. What is parse identifier doing? Local index, resolve local. So that's an identifier that already exists. But for a let, we want to declare something always. Declare variable. So declare variable is only being called in parse symbol. Don't really want that to be the one, though, that returns that new index. This just doesn't feel right. So parse let. Let's go back and see which functions we are calling here. So parse symbol, define variable, compiler define variable. So this seems to be the right place for that. So compiler define variable. If scope depth is greater than 1, here is where we could return an integer. Compiler local mark initialized, local mark initialized. You know, that's actually pretty good because we can make an assumption here basically that it's this one basically because we just initialized it. Local mark. Yeah, we're just gonna return the same thing. How about that? We can do it right there. So uint8t. Now define variable. Where else does this matter? Define attributes. Emit bytes, define global variable constant. That's the index of the constant. Yeah. Hey, Felipe. We're going to return a 0 there. I don't know. That's probably not a good thing to do. What does this really mean? Great idea. Okay, so define variable ex. This function also needs to route that through. So define variable needs to return this, uint8t. Now define variable, we call it right here. That's the one. Okay, good. So local is coming from that. And then emit bytes set local. Local index. How about we call it that so that we're a little bit more clear. And then let's compile this and see what happens. So constant set local, constant set local. That looks right to me. Let's also change those values in the test because I want to make it really clear what we're looking at. So this can be 3 and 4. This can be 7. Let's run it again. All right, so now we see that the constant we're pushing is 3, and we're setting the local with index 1. Constant 4 is being set, and then we're setting local to 2. Reading local 1, reading local 2, and we're obviously not doing the add operation there for some reason, which is really strange. It's just you're calling pop scope 3 times, which is very wrong. So let's see. Let's go back into compiler. Pop scope. Where's pop scope being called? We end the scope. Pop all the local values off the scope. Retain the final expression result. So, seems we're doing that here also, which doesn't make a whole lot of sense. But let's deal with that later. Okay, so first of all, the problem we have is that we're not actually using the values that we are setting and then reading back. So why is that? Let's check into compiler.c and then look into the body of that let. So parse let. So around here, parse block. Okay, printf before parsing block. And then we can say after parsing block, just to sort of get a sense for what we're doing. After parsing block. I think I got another bug in here now that I think about it. Parse list. I think this is why for sure. In this function, I did not add something important. Parse operator call. Okay, so that is right. I'm pulling the subkind. Printf parsing add. Let's say here parsing operator, just to make sure we're getting to the right place. Parsing operator. Whoa. Okay. Parsing operator. All right, so call token sub kind. Let's get a little read on what we're doing there because we're obviously not hitting the add. All right, the sub kind is 0. So how do we even get in there? Operator call. Is call is false. How is call being set to false? Is call. Parse the first expression if it's not an operator. Symbol and token kind none. Call token kind is. Okay. That's weird. So what's the symbol kind then? Let's see. Let's do this really quickly. Call token. Come on. Token kind. All right. Operator 15. I think something must be going wrong there. That's interesting though. So let me check my scanner code. Token kind. Oops. Token kind plus. All right, so scanner make token kind plus. I see. So that one is not being treated as special. I got a little bit of a consistency issue with the way that I implemented this sub-kind magic. I think that's part of the problem while we're hitting these issues. So make token. What else do I have in here? I have add, subtract, multiply, divide, and or not. Those are definitely using the subkind. List is. All these others are using it too. So the math operators need to be consistent. All right, so what I'll do, make token. All right, let's do it this way. Make token symbol. Come on. Make token symbol. No. Token kind. What? Scanner make token. So we're setting the subkind somewhere. Subkind. That's in read identifier. read identifier. Okay, so is alpha. Okay, cool. That makes sense. So here we need to scanner make token. Trying to avoid extra complexity in the places I call this, because I don't want to do this multiple times. Token kind is not symbol or keyword or true or nil. All right, here, look, I'm just gonna do it the easy way, then I'll go clean up the code later whenever you're not watching over my shoulder. Okay, so token equals, we're gonna have to do this as well. We're gonna join this line, and then we're gonna say token, no, symbol. I don't like this. Token.sub kind equals token kind plus. All right. I wonder if I should set the sub kind to the same thing if it's not a symbol token. That would solve this problem immediately. Okay, maybe I'll do that instead. It's also dirty, but at least it saves me from having to change the code in a bunch of places. Make token, sub kind equals kind. How about that? So now add shows up, which is good. But we're still popping too many times. So the whole thing about this pop scope is we're trying to pop all the locals off the value stack, which probably begs the question that we need to be able to see the value stack too. So let's go into the VM and turn on the debugging of, or the tracing of the execution, so we can see what's on the value stack. All right, so here on the value stack, we start with the script. We push 3, we push 4. You can see right here. Oh, interesting that we aren't popping those constants back off after we add them. That's kind of nasty. So we're pushing 3 and 4. We got 7. Then we use pop scope to push pop both of the locals off. Then pop scope gets run one last time. Okay, that must be a bug. That just doesn't seem right. Let's go back into compiler, pop scope. So I think that just must be invalid. Now it evaluates correctly. I'm still very unsure about why this is here twice, but it seems to be working. So, oh, those are the locals. We'll leave those there. Okay. Okay, so now at least the code executes correctly. I'm going to take that out because that doesn't seem right anymore. That must have been held over from old code. Now, if we go back to VM, turn off trace execution, this is what we're targeting. This is what we need to write a unit test to check. So I'm going to copy that code there, go to test compiler.c, and then I'm going to paste in this little snippet, and then we can just basically write the same checks for that. So we'll replicate that 3, 4, and then xy. That's fine. So we want a constant of 3. I'm trying to think, is that the right way to put that in? Yeah, constant 0, constant 1. Yeah, we need to check the constants too, which we don't actually do yet. We may have to put like a check constant, which would be a nice thing to do. Then we don't call list. We actually call set local on these. So op set local 1. So we want to set the first local value. And here we'll do this too. 1 and 2. And then we need to read the local for both of those because we're going to use them in an operation. Read local, both for 1 and 2. Okay. And then we want to do 1 byte for add. I need to check these two bytes. Bytes. Okay. All right, then we're going to check the byte for add. Then we're going to check the pop scope, which really should just be a pop. Now I think that that pop scope was sort of a theory I had, and I don't know if it's really worth it at this point, but we'll see. All right, so I think whenever I implemented closures, the pop scope thing was no longer useful. OP return is definitely at the end, but we need a couple pop scopes. So we're going to drop that. And in fact, let's just do this. Pop scope. Pop scope. So we're really just checking the bytes that have been written for that function in compilation, just to make sure that it does what we expect it to. So let's run that now. One failed. Okay, so what is wrong here? The expected pop scope got 7. Did I put something in the wrong order there? Constant, set local, read local, add, pop scope, return. Let's see. So what is 7? Let's look at the operations here. 0, 1, 2, 3, 4, 5, 6, 7, add. Okay. So what are we actually getting? That seems wrong. Test compiler. So constant, set local, read local. Oh, I deleted my add, obviously. And that's that. Now that test pass. Okay, so now we at least have a verification that let works, which is good because this has been something that has caused me trouble a couple times in the past while working on the language, especially when I started adding closure support. So now let's do the same thing with named let. Named let should be working correctly now. So compiles named let. We have a similar output, which looks much better compared to what it was before. Here, OP constant of, let's see, 0 is the one we want. Then OP constant, no, we don't need that because we only have one constant we're putting here. So OP set local for the first local slot. Then we need the read local for slot 1 because we're going to use it in that add operation. We need to add bytes there. And then we need another constant because we're going to push another one in for that 1, which actually, let's make it a 2 instead, just to make it clear. And then we need OP add, then OP pop scope. Whoops. So this is not a very test first approach whenever I'm just like looking at the output and writing a test to verify that it never changes, but it is still valuable nonetheless. All right, so that verifies cleanly, which is good. Okay, so now, how should this output be changed now that there is a new let, or sorry, a name for the let? I think that means it really needs to be another local variable that gets defined in the scope. So maybe we need to define that as a local so that it can be referenced in the scope. That definitely sounds right to me. So it's just going to be another local that gets defined in the scope. So let's go back to compiler.c, parse let, and then for that let, we need to basically declare it. So there's a compiler parse symbol there. So in this case, we could probably just do the same thing. Compiler parse symbol. Now, parse symbol, does it return the symbol? No, it returns an integer. Do we need? Let's see. Parse symbol. Returns 0, okay. We don't need the actual name. What we do need is the slot number, I think. That actually makes sense. So maybe I can store the slot, the self-referential slot inside the function. All right, let's try that. So parse let. So we're not going to store the let name. We're not going to worry about that. What we will do, though, is uint8t let name slot equals 0. So we're going to parse the symbol, same way as we did before, down here. Let me check this really quick. I think I need to do this first. The current is symbol. We need to advance first. And then we parse the symbol, and then we store the local for that symbol. Where am I? Okay, right there. All right, so we're actually going to store this into the let name slot. So I'll just delete this little part of the comment there. That's not really needed. All right, so parse the let name, and let me put the slot in here. Let name slot. Store its local slot. Now let's try this. Okay, so we got a little problem. Expected type byte OP constant got 24. Define global. We do not want that. So what are we doing wrong? Oh, we haven't begun the scope yet. So let's actually do that first. All right, so start a new scope for capturing locals. Still not happy. Expected byte 1 got 2. That's right. So yeah, I need to shift the local numbers because we've got another local now. So this needs to be local 2. And we also need a couple pop scopes because we need to get rid of that local that's on the set. So now this is good. Nice. So if we were to refer to test let somewhere down here, then we would be able to, let's see. Let's just write this out as an example similar to what we had before. So if greater than 3, or let's see, greater than 5, if I is greater than 5, sorry, brain fart, then we want to have, wow, this is just making a total mess, isn't it? If it's less than 5, then we want to call itself test let +1, right? And otherwise, we want to exit. So we can just say return I. Let's just do that. So what was return I as the last thing that happens? Okay. So that should be a usable snippet. If I just do that part. Okay, that's good, that's good, that's good. Now this is all going to fail when I try to compile this, but it's going to be interesting to see what the output is. Okay, we got a little bit of a seg fault, which is interesting. Address sanitizer is catching it. Let's see, line number 73. Let's take this out for right now, just to see what's going on. All right, so the output for, and another thing we'll do, we'll go back into test main. We're going to take that VM suite out to reduce noise. We can also take out the let just to get to one test. Reached a compiler error. Interesting. Okay, so we didn't get any output. Let's see. No indication whatsoever, which is great for a language. Test compiler, let's see. Let test let I in 1. Said it was in line 1, so it must have been that. Okay, maybe I should simplify this first. So let's just say test let. This is going to be an infinite function. I1. Let's just see what this does first. Okay, so we got an output on this one. So constant 1, which is the one we're setting into the local. We read the local 1, which is good. It's recognizing test let as local 1. Read local 2, which is the value for I. And then we put a constant for 1 to add them. And then we call that test let on the result. So that's our call. which is what we want to replace with a jump effectively after we've determined that this is a tail recursive function. And then we pop the scope a couple times after we call and then return. So that is correct output for the non-recursive case or non-tail recursive case. Now I wonder why we had the issue of it not compiling this part. So let's just say 1, 2. Just see. Let's see what we can find out about the failure here. Yeah, that still has a compiler error on line 1, which doesn't make a whole lot of sense. Maybe if I put things on the same line to see what happens. All right, so I will join these together. Probably not going to help, but let's just see what happens. So if... Let's see what this does first. Okay, it says there's a... yeah, I need to check if there's a compiler error because obviously that's a failure case. Compile... So if, where is it? Yeah, it doesn't actually tell me, does it? If out func equals null, which I think is the case if you have a fail compilation. Fail, compilation failed. Oops, let's not make it yelling. All right, and then slash that. So that should be enough. Let's see what this does now. Okay, compilation failed. Good. Just to make sure we're not, you know, getting bad results. So I'm curious why this failed. Oh, do I not have a greater than operator? That's fantastic. All right, so how about this? If is equal. Let's do it that way. How about that? That must be why. Yeah, that's got to be why. So we got some jumps in there for the if now. All right, so I can put this back in since I know what the problem is. So we'll just say equal. There you go. And now parse it one more time just to make sure everything's good. Okay, so now we at least have a starting point. That's a lot of instructions there. It's gonna kind of suck to write that out, but whatever. Okay. So what we want to do is figure out how to turn this into an optimized tail call. All right, so first let me just go in here and maybe write some of this out because I do want to verify that the output is correct. Because we want to make sure that it will catch something that's kind of a little bit lower in the list. In fact, I don't want to make it too complicated now, but all right, so let's go to right here maybe. Split it a little bit so we can see things better. Okay, so constant 0, set local 2, read local 2, constant 1, OP equal, because we're trying to check the equivalence of those values. Then OP jump if false. Now, I don't remember exactly how that instruction works. Let's see. Let's go to disassembler. Jump if false. So this is just a jump instruction. All right, so jump instruction has extra stuff. Jump. Okay, so, okay. So it has 2 bytes after the instruction itself. I'm not really too worried about the values of those, but it is 9 to 26. Does it pull those values out? Slot 1, slot 2. Yeah, it does some calculations. All right. Let's think about that for a second. So jump or, and we're printing out. So the sign is the first jump instruction. Okay, sign is positive. How do we know for sure? All right. So we're printing the offset first, start offset, and then the jump offset. So what I really need is to validate that those are correct. Okay, so that's what I'll do. We'll go into test compiler. We're going to say check jump. And what was that jump if false? Seems to have the same effect. So define check jump. Byte 1, or how about this instruction? Source dest, I guess we could say. And then we paste this in. We kind of need to do this in line, which is not great because I don't want to define a variable for this. Maybe I have to. Uint 16t jump val. Have to have some state variables to do the checks because I'm doing this all in macros to make it easier to write out information about where things are failing. All right, so jump val equals. Then we'll delete this stuff up until this point. Now chunk. We need to pull this little bit off here. And then this is a dot. Okay, so that starts the value we're checking. And then jump val. All right, drop this right here. Turn this into a dot. Now, so we have the jump val. Then we can do the check. If, come on now. Out func. Let's just copy that. No. We need to check the assert. What was it? Assert equal in test.h. Assert int. We could try that. Assert int, and I didn't think to check what the order of the values was. Assert int expected and actual. Okay, so expected would be source, and the actual would be this part right here, I think. Now let me double check in disassembler. Jump instruction. 4D is offset. So offset itself is the beginning. Oh, okay, that's the beginning position. So the position where it's actually starts, the offset itself. And that would be at byte index. So expected would be byte index. Start location. And then the end location is that whole offset plus 3 times sign times jump, which is pretty funny. This code I got directly from a book, so I'm not an expert on what's going on there. Obviously, it's offset +3, which is the 3 bytes that are written for the jump instruction, times the sign, times the actual the jump value, which I guess is the number of. Well, we're multiplying by it, which is kind of interesting, actually. Times jump val. So jump val. Yeah, this is not the best code I'm writing here. We don't have a whole lot of time left. Byte index offset +3. We don't have an offset. We have byte index. This is going to be a horrible failure. Maybe I should just do this for now. Let's not check the values because I think I'm going to have trouble with that because I'm not doing this calculation correct at the moment. So what we're just going to do is make sure that it has the right instruction. So we're going to check byte 1 as instruction. And then we're going to skip ahead by 2. So byte, or by 3 actually. No, by 2. IDX plus equals 2. Just to get us back in the right place. All right, sorry about that. Okay, so here, it's this one. OP jump if false, check jump. And then 0, 0 to do fill this in. Actually, I think I can tell where that is. So 9 and 26. Okay, so at least we have that part. And then a pop after, which is just a single byte. And then the next set, some more read locals. Yeah, this is just so much stuff, man. Needs to be a better way to do this. So 2 read locals after the pop. That's for 1 and 2. Then a constant for number 2. And then an add. Probably should have picked a better simple example. Let's just power through it. All right, so OP call 1. Actually, we haven't done a call yet, so this is where we're gonna have to change in a moment. So call 1 and 0. So this is actually something new that I did. We're gonna do a check call. Arg count, keyword count. So we have 2 values that get passed in. One is the argument count, one's the keyword count. Check byte OP call. This one is more obvious, at least. And then arg count. And then keyword count. Okay. So now we'll go back down here. The OP call should work. 1 and 0. And then the next part would be the jump. Check jump. OP jump 23 to 29. Another pop. Where is it? Oh, that doesn't need a 1 there. Another read local, 2 pop scopes, and a return. Okay, so I think that should have us fairly in line with what was there before. We'll have to double check that. And you may be asking why? Why do all this right now if we're just going to change it? Well, we just need to have something as a starting point to verify. Okay, so we did get all that back out, which is good. All right, so now if we make a change on this whole test let thing, and in fact, let's go ahead and stage some of this stuff so that we don't lose it. I'm going to stage that part. Interesting that it tweaks some more indentation. Looks like my code formatting is not working the same on multiple computers, which is a very nice thing to have. So it's similar to what Alex was talking about earlier. So that's really the one we need, right? Some of this stuff probably should be done too. Let me go and tweak the stuff that needs to be tweaked. This function we don't need. Yeah. Add local. Did we end up using that after all? I don't think so. Screw it. Okay, so we have the index of the name of the let. So let's check. So one thing that occurred to me at some point is that it might be better to turn this into a lambda effectively. So a named let should probably turn into a lambda and not be treated as its own local scope. So you can treat it like a named function that is defined anonymously, sort of in the local scope. Or even create a scope with a local with that variable name, and then yeah, I'm trying to think of the right way to approach that. We can just hack it in first. That might be better. Then we can deal with the other part another time. All right, so inside compiler, we've got the named let here. And then before we go into the body, we need to do something to sort of hold on to which slot is the recursive call. So inside the current function, let's say, and inside the current scope, this all needs to be done statically. So it's done in the compiler. So we know that inside this function, we're going to set some state, and then we're going to undo it afterward. Because all that matters is that the compiler knows that a particular local slot is the one that holds the self-reference, and if it finds a reference to that local, it should turn that into a jump instead of a recursive function call. So what we really need is two things at this location. We need to have the index, but also the offset, so we can jump back to the instruction at that point. Actually, we need to jump to the instruction after we set the locals. So in this for loop, we're setting the locals, and really it's right here. Okay, I think it's right here. So store location to beginning of body, or offset to beginning of body, and the let name index. So if let name index is greater than 0, we would want to do that. And then we can store that inside of the current function, I think. Yeah, because anytime you do a recursive or any other kind of call inside this, or another lambda, let's say. Let's check that out really quick. OP call. So do we have any other state? We call into another function, then it's irrelevant, I think. I'm trying to think if there's like a stack we need to keep, or if this only really matters inside the immediate body. So inside of a block, you can give it the information about what to look for in a recursive call. And we're using this parse block, I think, function for this. Hey, Porf. So parse block. Let me just take a look at that function really quick. So parse expression, compiler consume. So inside the block, any call here to the current function name here should have its parameters set back on the local slots. Yeah, it really makes me think that this needs to be done with functions and not with sort of like the local scope, because we're not gonna be able to generalize this unless we do it this way. So in a function, so let's say we have a function in object.h, object function. We have some information about what this function is, the type of the function, the number of parameters it takes, the up value count, which is basically the count of variables we've captured in a closure, or maybe the variables from this function that have been captured in a closure. The chunk, which is the actual bytecode output for the function, or bytecode definition of the function. The keyword argument array, if you have keyword args, and then the name. So the name is important because we would be able to use that against a local to say that it's doing a self-reference. So if you have an anonymous function, a seemingly anonymous function, then you could store, which is created for a named let, then you could store its let name in this object string so that it can be used inside of any logic. I think that would be a lot easier to manage than what I'm trying to do right now. So we would basically create a new function definition or declaration or whatever you want to call it, which would create a completely new function object. And then at that location in code, we would make it self-evaluating, where you would pass in the local variables as parameters of that function, and then the function would be populated with the let name. So let's think about that for a second. Maybe the parse let is a specialization of parse lambda. So how similar are these functions? We create a function context. We create a scope. We don't deal with keyword arguments. So this is slightly different, the way this works. Yeah, in a name let, you would have to pass in the binding values as the function parameters, effectively. And then eventually we parse the block. And then we deal with closures, which actually may be not entirely relevant, I guess, because you're not going to pass this function anywhere, so you don't need to deal with closures in that case. So there's another use case of parsing a lambda, there's a few things you would want to turn off. You don't want to deal with closures because you don't have to, because it's local, it's locally defined. You also don't want to deal with keyword arguments or define attributes. So I don't know if it makes sense to even try to reuse what's there. We may have to do a simplified function context creation. But then again, if you have nested lets or a let star, that is kind of like nested function scopes. So you may need closures from that perspective. because you need to get to the values from the parent let context, which opens a whole other can of worms. I'm just trying to go through these steps of deciding what to do if I do turn this into a function situation. If I don't do that, if I try to keep it simple, then let's see, parse let. Let's go back and see what I would need to do in that case. So in the body, somehow parse block would have to have some context about what local it's looking for. So that inside of the parse list function, when it's trying to call something, it can say, oh, okay, this is not actually going to be a call. This is going to be a jump instead. So we need some kind of state. And really, the function is the best kind of state for that. The function object, because we could add the information about where the actual beginning of the body is. Yeah, it seems like that might be the best approach. Obviously, we don't have time to go through that whole thing, unfortunately, because it's going to take some time to write that out, I think, and also to get it right. So the way that I would have to deal with that is probably to write a customized function creation routine here just for let itself, which seems terrible. I mean, like, you shouldn't have to do that. But, I mean, it would be nice if let could be a macro. But then still we would have to deal with slightly different behavior for function declarations that are they're recursive and also named lets because they're not exactly the same. I'm debating on whether I'm going to actually try to jump into this in this function and just try to make it work. So, oh, let's go back and do this. Parse let. Sorry about that. So let's say that we were at this point in the function. We have the let name index, and we also know what the offset is currently. So that's in the context function. What is it? Chunk and count. Was that right? Chunk. Offset. Where's offset coming from? Okay, offset, patch, jump origin. Yeah, so some of this jumping stuff is pretty similar to what we were thinking about. The origin is emit jump. Okay, so it's chunk count, right? That's the location. If I can go back to where I was. All right, so chunk count. So this is the position. So uint 8t. I guess uint 8t, right? Isn't it? Oh, it's an integer. Okay. So int body start. So this is sort of like the body start location. So if we can save this information somehow, or even pass it in to the block, or set it on the compiler context. But what would the compiler context do with that information? I'm trying to think if nested function definitions would have an effect on that. Like if it would need to change or be restored like a stack. If you have a nested function definition, it should clear out whatever the values are. And this could be information that's on the C stack here as we're compiling. So if we pass this into a function as a parameter, or maybe set it on the context. But that just feels a little bit dirty to do that. So if I came up with a hacky way to do this, could I also use it for functions? If I were to do this with normal function definitions, I would probably just attach it to the function object itself, because that has all the context that I need. So yeah, I think ultimately I have to do it with functions. I don't think there's a way around it. I think I'm gonna have to do a similar thing. So let's just try it real quick and see how far we can get, because we don't have much time. But I don't want to leave this stream sort of half done in the sense that we didn't really do much. All right, so parse lambda inner. We need to create a new compiler context. In fact, yeah. So create a new compiler context for parsing the let body. Okay, func context, we'll call that let context, init context. So we're not going to set anything yet. Compiler init context type function. We're going to treat it as if it's a function. That's all good. So parse, come on, lambda inner. Okay, so let's pull this down here. Compiler.c. And then we're going to jump this back to parse let. We just want to be able to see these things side by side a little bit. So we're going to ignore all this keyword list stuff. Then we're going to, let's see, compiler advance. Yeah, the tricky part about this is that we're going to have to sort of split up how things get done. We either create a function, we're going to have to put it on the stack immediately and then parse the arguments. But that's possible. That's possible to do. We could do that. Okay, let's take a look at this first. So default value pair, whatever, parse symbol, define variable. That's similar to what we were doing before. Default constant has default. What is this for? It's not in the, oh, okay. This is what we want, right? Okay, that's the part that is for arity, non-keyword parameters. Okay, so that was a for loop. Parse lambda inner. Okay. So that's in a for loop, which we do have here. Similar thing, we're checking for the right paren. Okay. So similar situation, if I paste this code, we're going to increase the arity of the function, which honestly is something we do want anyway. So I think this is the right approach ultimately. We're going to need to do it this way. So let context. Let cannot have more than 255 bindings, which is a reasonable thing to say. Increase the binding count. Okay. Left paren, increase the binding function argument count. All right, we do want that. And then compiler advance and parse symbol. So this is, wait, where am I? Yeah, we're in the right place. So that's what we were doing before. Parse symbol, we're storing that as a constant, which is kind of interesting. I don't know why that's the case, but let's just go with it. I guess I could just steal that code. Let's just do this. Local index equals defined variable. I don't think I need that either, do I? Oh, I'm doing that with a constant? Interesting. Let's go with it and see what happens. I'm curious to see what the outcome is going to be for this. And then this expression needs to be parsed as something else. So to do the binding value needs to be a function parameter. So I'm not sure the right time to do this. We need to have a function that we've created already, which I don't think we can do until we've already gotten through all the arguments, can we? Compiler parse block function equals compiler end function context. So we have to parse the entire function first, including the body. Then we have to parse all of the argument expressions to be able to pass those in as values. So I'm trying to think of how to defer the parsing of the arguments correctly. Because I don't want to copy them to hold on to them. I need to parse them soon. Maybe I hold on to a list of constants. But then it sort of defeats the calling. Yeah, I might have to go back and patch it in, actually. So one thing I could do in the current function context, or in the context where this function is being created, is I could skip the call. Yeah, so here, let's do this. Okay, so before parsing arguments, well, yeah. Skip ahead to enough space to put a call, but save a pointer to the offset. So we can come back and insert the call after we have a constant for the function. So that's sort of what we need to do. You see integer call offset equals we want it in the original context. So the ctx function chunk dot count. So that's the location where we want to go write it back to after everything's done. So that seems right. So we store a location to the original location, sorry, a location to where the call needs to be. Then we go ahead and parse that new function. We've got a new context where we're parsing all that function stuff. Actually, maybe it doesn't matter because it all depends on which context I'm using. So I start using the let context immediately to parse all the arguments, which puts it in the right context, the new function context that I'm sort of creating on the fly here. And then by the end, I will call like parse block and then compiler end. That may actually make sense. But yeah, it's, oh no, that actually, okay, I need a little bit of both. A little bit of both, I think. So what I'll do, parse the body block into the let context, end the let context, and then emit the bytes for referring to the function, or maybe even the closure. I don't know if I need a closure there, but maybe since everything else uses closures, that's what I'll stick with. So make constant object value function, compiler make constant op closure. Oh, okay, that creates a closure right at that location. And then we need to, interesting. We emit bytes at that location, but we really need to emit bytes at a prior location. So to do place the closure and constant rights at the call offset. So we need both of those. We need a constant to pull the function we've defined, and then we also need to wrap it with a closure at that location. Maybe we may skip doing that. So at the same time in this execution, what we can do is use the let context to parse the symbol, and then use the original context to parse the value. Yeah, that seems right to me. So parse the binding value into the original context where the let function will be called so that it gets passed as a parameter to the lambda. Okay, so I think that's the right starting point. I don't think we're going to finish this today because I'm out of time, but this seems right. Once we get this function written, which I'll probably do off stream just so that we can keep making progress, so that next time we don't have to deal with all this again. What I'll do is finish writing up this function so that we are creating that inner function, setting up its parameters correctly, setting the name of the function so that we can check to see whether the local we're looking at is the name of the function itself, and then be able to write out the proper jump, in that case, back to the top of the body of the inner function. I think that would be enough to encapsulate everything that's needed. So let me just write out some of those thoughts really quickly so that I don't lose them, and then we can be finished with that. So let's see. Add a compiler support for named let expressions. We did that to some degree. Unit test for checking named let compilation. All right, so we didn't do the tail call checks. So next steps, finish writing let function parsing let lambda. Finish call offset patching after lambda is created. And then set function name based on let name. And that will work in both cases, actually. Will also work for declared functions. So in the context of a function itself, if we look at the name of a symbol and say, oh, this is the same as the name of the function, then you know that you're looking at a recursive reference to that function itself. So I think that's enough to take care of both cases with the same basic implementation. So the parsing code inside the body of a function or a let doesn't have to know which one it's dealing with. It just knows that it's looking for the name of a function and to compare a symbol. All right, so that's gonna be it for today. I apologize that we didn't make more progress, but like I said, this is the first time I've tried to write tail recursion before, and we had a lot of problems we had to deal with first before we got to it. So next time we'll have this hopefully working to the extent that we can start using it to start writing some of the code for either generating the build scripts for compilation, or if I've already gotten that done by the time we get to the next stream, then maybe we can start pulling in some of the game code. We can start writing a basic game engine to re-implement the crash to stack game that I did a couple years ago. So that'll be a lot of fun. Hopefully that'll be a more interesting stream than this one was, but keep an eye out for that on Thursday. So thanks a lot for being here today, folks. Those of you who stuck around this long, I really appreciate you. And until next time, keep it creative. We'll see you.